got me singing melodies I never thought I would. I'm feeling sorry for the homies who be smoking wood. Top, break it down for a player like Yee.
Welcome everybody to Chemistry 51C here at UC Irvine in the fall of 2020. This is our 20th lecture, and we've been talking about the chemistry of enolates. It feels to me that everywhere I look, I'm starting to see stores that advertise CBD oil, CBD, and they usually have pictures of marijuana leaves and crosses that look like hospital symbols, which seems rather misleading to me. But some of these stores, which I love, they have rudimentary chemical structures on them, and I love that. I love going to grocery stores and seeing molecular or organic molecules or storefronts, and even if they don't get it quite right or they're being stylistic, I love the fact that people are willing to draw organic structures, right or wrong. That just really excites me, and it opens up conversation. So let's talk about CBD and what's going on with this this compound. The CBD stands for cannabidiol. So cannabidiol is a member of a class of natural products called cannabinoids that are found in marijuana plants. But I want to be a little bit more specific. They're common to a species of plants that are known as cannabis sativa. And you've heard probably of two members of this class. I'm not sure whether you would call them cultivars or just variants, but hemp and marijuana are two common members of this species of plant, cannabis sativa. And so I want to talk about the difference between hemp and marijuana and the compositions, the cannabinoid compositions of those two types of cannabis. So first of all, hemp, when I hear the word hemp, I'm usually thinking hemp rope or hemp fabric. Hemp is mainly grown and harvested on a large scale because it's a source of fiber for making old-fashioned hemp rope, or as I said before, you can make fabrics out of those. So they grow these on large scale for fiber, for animal feed, for the oil content. And that's distinctive from marijuana. And when you look at the oil, if you were to use hexane or something to extract the oil out of hemp plants, and you looked at all the cannabinoids that came out of those plants, just grouped together all the cannabinoids that you could extract out, you'd find that 20% of the cannabinoids are this molecule referred to as cannabidiol or CBD. And that's what they're selling at these stores that advertise CBD oil. They sell you vegetable oil that's been doped up with cannabidiol that's been isolated from hemp plants. But there's another variant of cannabis that is much better known and notorious, and that's marijuana. If I showed you, if you're not a marijuana grower, you probably wouldn't know the difference between the full-length plant of marijuana and a full-length hemp plant. But when you extract the cannabinoids out of marijuana, what you find is that there's still quite a bit of CBD in there. Over 10% of the cannabinoids in a marijuana extract are CBD. But when you look at the THC content, and this is the stuff that gets you high when you smoke marijuana, it's the tetrahydrocannabinol, and specifically the delta 9 variant. That means there's a double bond between positions 9 and 10. I'm not sure which of these positions is 9 and which of these positions is 10, but the delta 9 tells you where the double bond is, which means obviously there's other naturally occurring cannabinoids that have the double bond at different positions. So when you look at the cannabinoids that are present in hemp, only a tiny amount of the cannabinoids are THC. So you're not going to get high by smoking hemp. Maybe you'll just get lung cancer is the only benefit of that because the concentrations aren't high enough. Now, when I look at the chemical structure of CBD, it's just inviting me to protonate this. If I were able to, let me switch back to a red pen here. If I were able to protonate this double bond at this position and leave a carbocation, this lone pair on the oxygen would attack that. And it seems like it ought to lead to THC. We ought to be able to synthesize THC from readily available legal cannabidiol. And so it seems to me, hasn't somebody tried that? If we're going to talk about stuff in this class, why not talk about synthesizing scheduled substances that are controlled by the FDA instead of some other topic? So I drew these structures into the Reaxis database. This is one of the databases that we use uh, here at UC Irvine in order to search all the reactions that have been performed since the 1850s. So I drew the structure of cannabidiol, that's CBD, and I said, show me every reaction that's been reported for converting that into THC. Has somebody done that before? And the answer is, of course, it's been done before because people want to make drugs. I found 10 reported reactions where people have carried out this transformation and studied it. Here's one that came from a patent. There seem to be quite a few companies that are patenting this process. And if you take cannabidiol, which you can extract out of hemp plants or go buy at your local CBD store, and you treat it with catalytic boron trifluoride etherate, that coordinates to the oxygen atoms and releases the protons to act as an acid catalyst. And the acid catalyst that's generated in situ catalyzes this transformation and generates delta-9 tetrahydrocannabinol, just like you get from smoking marijuana, in about 70% yield, maybe a little bit less. So, right, if you want to go buy a bunch of CBD oil, unfortunately, they put it into vegetable oil, meaning it's harder to get out of there. So who's publishing these types of things? Who's patenting these types of procedures? I looked at this particular reference at the patent. It was some company called Euroceltic, not a regular pharmaceutical company, which surprised me. So I typed that name online. It turns out that Euroceltic is a holding company of Purdue Pharma. That's the company that's been excoriated in the media and in our country for marketing hillbilly heroin and getting the entire country addicted to legal forms of heroin that are slow release version. So now they're turning away from heroin because they've been sued like crazy. Looks like they're turning to cannabidiol and making THC. Okay, so cool chemistry.
I'ma keep smoking till I reach my peak. Or till I'm stuck and my body feels weak. Headed down to the dungeon, wondering.
Right, let's turn back to where we left off. Just to remind you of where we were at. When we left off on Friday, we were talking about making enolates and having them attack carbonyls, and specifically esters, making enolates out of esters using alkoxide bases, and then having them attack esters. And those reactions are especially good when they're intramolecular, when you can make an enolate and then have that enolate attack another ester to make a 5 or 6 member ring. We call that a Dieckmann condensation. It's an intramolecular variant of the Claisen condensation, and I expect you to know the Dieckmann condensation. But let's go ahead and move a little bit further and talk about another reaction of enolates, and it's a reaction of stabilized enolates. Like the ones, for example, the ones where you have 2 carbonyls stabilizing those anions. Those types of enolates are so stable, you can't even protonate them by putting them in water. And when you take those stabilized enolates, and you put them in the presence of enones. And let me just, to help you remember, I want you to recall that way back in chapter 20, we taught you that cuprates add selectively to the alkene of an enone, not to the carbonyl. And that's a selective reaction. I expect you to know that special reaction of cuprates. And in the same way, these types of super stabilized enolates, where you have 2 carbonyls next to each other, or a carbonyl and a cyano group, or a ketone and an ester, those types of super stabilized enolates will attack not the carbonyl carbon, they attack the alkene carbon. And so I'll push the arrows here. I could have pushed the arrows all the way into the carbonyl oxygen, but I'm just going to leave them there. And so the product the intermediate that you get out of that initial mechanistic step, I didn't leave a lot of room for that, but let me try to sketch that in here. You got to count the carbons here. It is so easy to mess up how many carbons are attached. And so you'll generate this intermediate enolate, and that will equilibrate. There's protons over here that are still more acidic than the enolate you just generated. And so you have to worry about exchanging enolate protons so that you take the proton over here and transfer it over to here, and then you've got an enolate that's so stable that you have to work it up with HCl instead of just water. So I'm specifying an aqueous HCl workup here. The book doesn't do that, unfortunately. Because the book, that should be spelled workup, because the book doesn't tell you you have to use an acid workup and it says water, I'll accept water here, but really you need to use an HCl workup for this reaction to put the protons where you need them. Okay, so that's a powerful way to make these bonds like this. So I expect you to recognize the pattern of reaction that results from an aldol reaction or an aldol condensation. And I also expect you to recognize when you can make these types of systems through what's called a Michael reaction. That's a conjugate addition reaction, a 1,4 addition reaction of super stabilized enolates to enones. Now, let me just show you that it doesn't have to be two carbonyl groups. We can have, for example, over here, if we look at this product and we wanted to know how would I make something like this using that same kind of a process. So what would the pieces have to look like? Well, what you need to recognize is that's the bond that you would form by doing what's called a Michael addition, this kind of a process of stabilized enolate. So I would need one enone that looks like this. And then I would need some sort of a stabilized enolate where it's not just one carbonyl here, but also another stabilizing group. In this case, it's a cyano group that's the second stabilizing group. Cyano groups stabilize carbanions about the same as an ester carbonyl. So you get about the same stability. So these two starting materials would, if you had the sodium salt here, the sodium salt or potassium salt, doesn't matter. This would easily do that same type of process where you add here, push the electrons down, and then you work that reaction up using some sort of aqueous acid usually. Again, I would accept it if you wrote water there, but really you need aqueous acid because you have super stabilized enolates floating around in your reaction mixture. Be careful here. You might have noticed that this generates two new stereogenic centers. And so this ends up being created as a mixture of diastereomers. I'm not going to draw those for you, but I expect you to recognize that two new stereogenic centers were formed that weren't there in the beginning. Here's one, here's the other. You have no control over that. You're going to get a mixture of RR, RS, SR, and I've already forgotten what the other ones were, but I expect you to recognize stereochemistry. Now, we have some powerful tools here with this Michael addition and aldol condensations to assemble some very complex molecules. So I'm going to show you kind of the piece de resistance of this chapter, which is this extravaganza of reactions that allows you to make six-membered rings. And this turned out to be a super important reaction in the 1950s and the 1960s when everybody was trying to figure out how do we make steroids without being forced to isolate steroids out of, I don't know, pig brains or pig spinal cords or slaughterhouse stuff where you get 2 mgs of steroid out of vast quantities of slaughterhouse parts. So the idea that you can make six-membered rings is built upon two reactions, the Michael addition and the aldol condensation. And you do both of those all in one step. So let's go ahead and take a look at this process. It's referred to as a Robinson annulation. So the Robinson annulation. And if you take an enone, so like the one down here, and notice that on the other side, there's a carbon atom that has alpha hydrogens. Not like on the previous slide where I had a phenyl group there with no alpha hydrogens. This CH3 has alpha hydrogens. So what's going to happen in this reaction is that if you treat this with a base like sodium hydroxide, then you now have a recipe for doing first a Michael addition. All right, let's go ahead and draw that out, that first stage of the reaction. And initially you generate an enolate over on this carbon atom, But that can get protonated and deprotonated and protonated and deprotonated in equilibrium. And eventually you're going to exchange. We'll walk through the detailed mechanism for this process. Eventually that can exchange to give a new enolate. So let me draw the product of this initial Michael reaction. Here would be the initial product of that Michael reaction. And I'll draw that methyl group down here. Now, if we had acidic H's here, the base that's present in solution would simply deprotonate there, and that would be the end of the reaction. But notice how carefully designed this reaction is there's a methyl group here that blocks this position. And so you can't deprotonate into between the carbonyls anymore. And so now the hydroxide that's still floating around, that was the hydroxide is catalytic, can now deprotonate at this position over here. And it can make a new enolate. So now there's no more acidic protons on your substrate. The only enolate you can make, let me just put parentheses around this because this is what you get after the hydroxide attacks. There's a minus there. Now the hydroxide is looking for places to deprotonate, and it protonates here and then reprotonates, and it protonates here and then reprotonates, and it protonates here, deprotonates here and reprotonates. Then it deprotonates here and reprotonates. But when it deprotonates here, that carbon atom is 6 atoms away. 6 atoms away from another carbonyl. And it can now do an aldol condensation. First an aldol addition and then an E1CB elimination. And so that kind of magic there produces in one pot. Whoa, that's the worst arrow I've ever, well, one of the worst arrows I've ever drawn. I'm not going to draw the steps on here. And that leads to an aldol condensation in order to generate this new CC bond. So if you start off with a ring or some substrate that has that generally has a group that blocks enolate formation here at this, generally you want it to be able to form one and only one enolate, and then has a carbonyl available that can undergo an aldol condensation. Why was this important? Because when people were searching for ways to synthesize steroids, and we now have some steroid drugs that are prescribed that are synthesized through total synthesis, that don't come from Percy Julian's Glidden process or the Syntex process, where you isolate steroid starting materials from yams or soybeans. We now make steroid drugs that we give to people from total synthesis, totally from scratch. And this was one of the first methods that was used to make what's referred to as the AB ring of steroids. And you can see that if you pick the right starting material, you could also append ring C onto another dicarbonyl. And so let's go ahead and use that example of this. How would you synthesize this 6,5 ring system, the CD ring system of the steroid, using this same Robinson annulation? And this will give us a chance to walk through the mechanism for the Robinson annulation. And it is a long mechanism. So on this slide, I've put for you the structures, and we can just fill in the arrow pushing here. So there's 3 stages to the Robinson annulation, 3 mechanistic stages. The first stage is the Michael addition reaction, where you form this bond over here. The second stage is an aldol condensation, where we form a bond between here and we condense, the aldol addition. And then the last stage is where you do an elimination. So let's go ahead and walk mechanistically through those various stages of the reaction. So you've got catalytic base in there, which could be alkoxide or hydroxide. And now we deprotonate. That position between those 2 carbonyls is super acidic. And it's going to have a pK somewhere on the order of 9. So I'm going to draw the electrons, I'll leave them here on this carbon atom. Of course, you could push them into the carbonyl if you wanted. This generates our enolate. And now we've got a stabilized enolate, and we've got an enone. Right? We're very careful to draw. This substrate here is so common. This substrate over here that it looks like this is so commonly used for Robinson annulations. We refer to it as methyl and then vinyl ketone, or MVK. If I go to any organic chemist and I say, oh yeah, do you have a bottle of MVK? They'll know exactly what I mean. So it's super commonly used for Robinson annulations. It's the most common substrate. So as soon as you see MVK in a reaction, look for base and a 1,3-dicarbonyl or something. And it's a very common substrate for Robinson annulations. Okay, so we've got this stabilized enolate. It's going to add, and then I'll push these electrons over here, and I'll leave them on that carbon. There's other ways to depict that. I could have pushed the electrons all the way to the carbonyl. And that leaves this enolate in the presence of, the conjugate acid derived from our base. Now I can pull the proton back off, and it regenerates our base in the solution. So there's the base we regenerated. Okay, so now the base is still present, and we still have this substrate, but now I don't have a superacidic proton. I've got protons here next to the carbonyl. Those are getting deprotonated, and then nothing happens. There's protons down here next to a carbonyl. Those are getting deprotonated and then reprotonated again. There's protons over here where we just pulled the that's going to get deprotonated and take you back over to this intermediate over here, but then it just reprotonates again. But when you deprotonate here, let's go ahead and draw that out. When you pull the proton off of this carbon, now it can do something interesting, right? As I said before, now that's set up to cyclize through an intramolecular aldol reaction to make a 6-membered ring. And so, and why is that? The number of collisions is so high. The frequency of collisions is so high that you're just likely to form 6 or 5-membered rings. Okay, so you generate this this alkoxide intermediate. Now that pulls the proton back off of the base and regenerates our base as the byproduct. So we have our base over here, and again, it's going to be pulling protons off of next to all the carbonyl groups. If you're wondering how come it only does this reaction here, we're not saying it only does that. But we're only showing you the steps that lead to the product you isolate in the end. So it is protonating here sometimes, and then you put the proton back. Sometimes you take the proton off of here, and then you put the proton back. But sometimes you deprotonate here. Right? If it was acidic enough to deprotonate up here, it's still acidic enough to deprotonate again down in this structure. So we can't really say why isn't, how do we know it's acidic enough? Well, it was acidic enough up above to pull off protons like that. And so don't do an E2 concerted elimination. That's not the way that aldol condensations work. You make the enolate first. There we go. And why is that so facile? Because the electrons are stabilized by the carbonyl. So we make the enolate first, and then in a second step, not one step concerted, but in a second step, we push out the hydroxide leaving group. And I'll go ahead and draw that out just because to get you used to the idea that hydroxide can be a leaving group in E1CB type elimination mechanisms very easily. All right, that's the end of chapter 24. What was chapter 24 about? In chapter 23 in our Gorzynski-Smith 5th edition textbook, we were making enolates and doing SN2 reactions. But in chapter 24, we've been making enolates and adding them to carbonyl compounds. Most of it was adding to carbonyls through aldol additions, aldol condensations, Claisen reactions where you're adding to esters. But then in the end, we showed you that for these special types of enones here, like this, systems that look like that, you get conjugate addition faster, better than carbonyl addition. And that's with stabilized enolates that do that. If you took just a regular unstabilized enolate, it would probably attack the ketone carbonyl instead of this beta carbon over here. Okay, we're not stopping here totally. We are. I'm just a little one of my screens here says that it's 9:41, which I don't think can be right. Let's go ahead and start on chapter 25. Let's start on chapter 25. It's the chapter on amines, and this is kind of the last chapter that we're going to cover. When we're done covering chapter 25 on amine chemistry, we'll circle back and cover one section that we left out of the aromatic substitution chapter. And that's nucleophilic aromatic substitution. I set that aside to the very end of the course to cover that material. But let's go ahead and take a look at chapter 25. This is our chance to get an introduction to amines today so that we can hopefully dive right in deep and look at some chemistry when we come back on Wednesday. But we need to cover this introduction to amines before we go further. Okay, now I want to start off by talking about two roles for amines. And let me go ahead and start off by drawing the same amine twice. And these could be protons or alkyl groups on here, doesn't matter. I've drawn 3 methyl groups. We're going to use 2 different words to describe this reactant. Right? The lone pairs on that amine are reactive. But depending on whether I attack protons, that could be a proton on a carboxylic acid, could be a proton on an alcohol, could be a proton on a protonated amine, like an ammonium ion, or depending on whether I attack a carbon atom, and that could be iodide leaving group, tosylate leaving group, doesn't matter. Could be a proton next to a carbonyl group, or sorry, not the proton, that would be above. But if I've got a leaving group and I'm making a bond, depending on the role, if I'm attacking protons, like here, I'm going to refer to that amine as a base. And so we're going to need to talk about equilibrium acid-base chemistry when we talk about amines, if we want to really understand the chemistry of amines. Down below here, if I'm using this to make carbon-carbon bond, or bonds to carbon, carbon-nitrogen bonds, now I'm going to refer to that as a nucleophile. I'll just abbreviate there. So the same reactant, and I'm going to use different words, either base or nucleophile, and just depending on whether I call it a base or nucleophile, you know what I'm going to do with my arrow pushing. You'll know what's going to happen in the reaction just based on the way I describe that. So again, so this is going to be super important, this idea that amines can have 2 different types of chemistry that can occur. Keep track of charges. Right? If I put an extra bond to that nitrogen, 4 bonds, there better be a positive charge in there. And we refer to that as an ammonium ion. An ammonium, when I have N nitrogen with 4 bonds and a positive charge. And you get the conjugate base. The important thing about deprotonating using amines is that these reactions are reversible. And they're fast. They're fast and reversible. So we need to know pKa's to be able to predict where does the equilibrium lie. This is essential, is that when we talk about deprotonating with amine bases, we have to think about pKa's and be ready to estimate which side of the equilibrium is favored. That requires us to know some pKa's. Now down below, when you attack carbon atoms, bonds to protons vibrate very quickly. Bonds to carbon slowly. It's slow to form bonds to carbon. It's slow to do SN2 reactions. And so when you attack carbon with an amine, relative to slow, and I should write slow. It can be relatively fast in some cases, but nothing like a proton transfer. And so when we do this, we're going to end up with ammonium groups, and we'll have some sort of a leaving group here. Tosylate, bromide, chloride in theory. If we did that. Okay, so there's 2 aspects of amine reactivity we're going to cover in this chapter. We're going to talk about acid-base or base-acid chemistry of amines and ammonium ions, and then we're going to talk about reactions where amines act as nucleophiles. And you've already seen in the chapter on carboxylic acid derivatives that amines can attack acid chlorides, or amines can attack carbonyl groups to make imines. So we've already seen some reactions where amines attack carbon. So it's not totally new. I would still call it a nucleophile if the amine is attacking a carbonyl. Let me just draw that down here, because just to be clear that, yeah, I still refer to that as a nucleophile when I'm attacking a carbonyl group. So let's not forget the addition to carbonyls, whether it's an acid chloride or an aldehyde, doesn't matter. Okay. So what about, but there's going to be one class of similar looking compounds that are really not similar. Let me just be a little bit more precise about how I draw that. So this lone pair may look just like the ones that I drew over here, but it's nothing. The lone pair down here is nothing like the lone pairs that I drew up above, the nitrogen lone pairs. We refer to this, it's not even called an amine functional group. Don't call this bottom structure down here an amine. We refer to this as an amide, right? This is an amide functional group. And the lone pairs are not at all nucleophilic. You're never going to see any reaction in this course where this lone pair reacts with any molecule. It doesn't act as a base. It doesn't act as a nucleophile. And that's because it's busy. This lone pair is already busy donating into the next door carbonyl. It's not going to react with any other proton. And so don't call an amide an amine. Don't use the amide nitrogen lone pairs to attack anything, right? Maybe you're better off drawing this other resonance structure. 40% of the resonance character of an amide looks like N+ with no lone pairs on there. So again, when you see a carbonyl attached to a nitrogen, that's not an amine, that's an amide. So distinguish the reactivity of those. So just remember that those nitrogen lone pairs, that nitrogen lone pair there, it's not basic, it's not basic, not basic, not nucleophilic. Right? Those lone pairs are dominating the carbonyl. Okay, so we're going to talk about acid-base chemistry later in the chapter, and we're going to talk about nucleophilic reactions. But we need to kind of get ourselves prepared here for what are some basic concepts behind the way we think about amines. So we need to talk about the potential for amine centers to be stereogenic centers. This is going to be a little bit complex. Let me go ahead and draw an amine. I could pick any amine that's got 4 different groups. The lone pair is considered one group. So since we're talking about controlled substances today, let's talk about methamphetamine. This is the chemical structure of methamphetamine. Speed, Adderall, it's the active ingredient in Adderall tablets that you that you buy from your friends to get ready for your exams. And there's 4 different groups on this nitrogen. So in theory, this methamphetamine has 2 different stereogenic centers. I think one of these stereogenic centers is obvious. That's this one right here. That's got 4 different groups on it. It's got nitrogen, H, methyl, and then a benzyl group on there. So that's an obvious stereogenic center. Let's just go ahead and point that out. So that's an obvious stereogenic center right there with that extra. Let me go ahead and draw the hydrogen there in case it's not obvious that there's a hydrogen attached. So 4 different functional groups, 4 different groups on that. But the nitrogen also has 4 different groups. But for reasons that I'm going to show you, we do not consider that nitrogen atom to be a stereogenic center in this course. So I'll just write not. And so let's go ahead and talk about why the nitrogen is not considered a stereogenic center. And the answer is relatively simple. It's because it is not configurationally stable, meaning that if I give you this one molecule of methamphetamine where the nitrogen has the R configuration, it will rapidly, without your control, interconvert between the R and the S stereoisomers. You can't control that. Let's take a look at that, at the bonding changes in bonding that are occurring when you start off with one amine, for example, that has the R stereochemistry. And let's just imagine that R is something with a higher priority than a methyl group. So this amine right here, if I draw the lone pairs, the lone pair right there, that one would have the R configuration according to Kahn-Ingold-Prelog nomenclature. The lone pair has a lower Kahn-Ingold-Prelog priority than a proton. It's got the lowest priority when you're trying to figure out R and S nomenclature. And amines very rapidly interconvert between R and S through that nitrogen atom. You can't stop it. It's fast. It's uncontrollably fast, even at room temperature. So what happens is that this thing almost flips over like an umbrella, kind of like when you do SN2 attack on a stereogenic carbon center. So I'm going to draw out a planar nitrogen atom in the transition state. I'm trying to draw all the groups on here in the same plane. And now the electrons in that sp3 orbital are now in a p orbital. I'll put one electron over here, one electron there, but there's phasing to the orbital, and quantum mechanically the electrons avoid each other. But that's planar. So, and it's very easy so this has 3 bonds in the same plane. It no longer has any stereochemistry. And so there's this very rapid, this is actually a transition state. There's this very rapid interconversion through a planar transition state that allows amines to lose any configurational memory they had. If it started off as R, it doesn't matter because it rapidly interconverts. R up here means like an alkyl group R. These will rapidly interconvert between R and S, and you can't control that. So I always tell you that you have to recognize when you form stereogenic centers and recognize when stereogenic centers are present in a molecule, but we're not going to consider amines stereogenic centers in this at any point in the field of organic chemistry. Well, that you're going to see in the field of organic chemistry. I had to hedge there for a second. Okay, let's go and talk about nomenclature. And I'm not talking about IUPAC nomenclature. I'm just talking about descriptive nomenclature, because we're going to run into a problem here where we kind of screw you with being inconsistent in the way that we use the terms primary, secondary, and tertiary. So I want to start off by reminding you how we describe alcohols. We have this useful description of alcohols or alkyl chlorides where if we have ethanol over here on this side, this carbon atom, we refer to that as a primary alcohol. And if you made a carbocation, it would be a primary carbocation. And if you converted it into an alkyl chloride using SOCl2 and pyridine, it would be a primary alkyl chloride. Over here, isopropanol is considered a secondary alcohol. So let's go ahead and write this out just to remind ourselves. This is referred to as primary alcohol. This is referred to as a secondary alcohol. And tert-butanol is considered a tertiary alcohol. Makes complete sense, right? When you look at alkyl chlorides, when you look at carbocations, when you look at the carbon atom and you decide whether something is primary, secondary, or tertiary. So now I'm going to come down to amines, and we use primary, secondary, tertiary when we talk about amines. But note what's going to happen when I describe these molecules. Ethylamine up above here is referred to as a primary amine, which kind of makes sense. But when you look at isopropylamine, for some reason, this is called a primary amine also. And when you look at T-butylamine, that's also called a primary amine. So what's up with that? How come it's different from carbocations, alkyl chlorides, alcohols? The reason is because the use of primary, secondary, and tertiary with amines is supposed to be referring to how many things are attached to the nitrogen atom. So we kind of switch things around on you. So if you wanted to talk about a secondary amine, we need to have 2 substituents on the nitrogen atom. So come back over here, and let me take this same tert-butylamine that was a primary amine. And if I want this to be a secondary amine, I have to put another substituent out here. This would be a secondary amine. That is now secondary. And if we wanted to have a tertiary amine, let me draw the most common tertiary amine that we use in the laboratory all the time. And that's triethylamine. This is one of the most common bases that we use in organic chemistry. And why is this common in organic chemistry as opposed to sodium hydroxide? Because triethylamine is soluble in organic solvents, and sodium hydroxide is not. We just don't use sodium hydroxide very much in the field of organic chemistry. regardless of what you've been thinking throughout this whole course, we use triethylamine much more commonly. It's soluble in organic solvents. So that's a tertiary amine base. And when we need a weak base, not like LDA, when you just need a weak base, not quite as basic as sodium hydroxide, but at least it's soluble, we use triethylamine. It's our most common base. Now, the book has a section on the physical properties of amines. Amines are kind of smelly. So when you take rotting fish, that's an amine that you're smelling. It's volatile. It's putrescine in rotting meat has an amine in there. If you buy ammonia solution for washing windows, you can smell this characteristic odor of ammonia in there. There's not a lot I can ask you about amines. They're polar, there's not a lot I can tell you about boiling points. Since I'm not going to ask you questions to memorize boiling points or features like that, I would suggest you read that section, but there's, other than some multiple choice question, there's very little that I could ask you. Now, usually on my exams, I ask spectroscopy questions. I'm not going to tell you what's going to be on my next exam or on the final, but if you look at every exam I've given in the past, I don't know how many years, there's always a spectroscopy question. So, guess what? I'm probably going to ask a spec question, but can't make any promises. I don't tell you what I'm going to put on my exams, but if you're a logical person, you could make a guess. So is there any spectroscopy that is specific to amines? Mass spectrometry, I don't put that on my exams, and there's a little bit that you can do with looking at a molecular formula or a mass from mass spectrometry and guess whether there's a nitrogen in the molecule, but I'm not putting mass spec questions on my exams. There is something you can do with IR spectroscopy to distinguish between amines that have 2 R groups and amines, or let me be more specific, amines that have 1 NH and amines that have 2 NH bonds. There's a specific signature in the NH stretch region. And so where NH stretches? NH stretches appear as these big blobby peaks, not as blobby as OH bonds. OH bonds are super intense and hydrogen bond alone, so they're blobbier. But NH stretches. So here's an example of a molecule here that has a single NH stretch in there, a single NH stretching mode. That's this peak right here, that little pointy blip there. And this turns out to correspond to this molecule. And that has a single NH. And if I look at other alkylamines that have a single NH, you're going to see that one little blip there. But if I take other amines, and this turns out to be a spectrum for, you guys probably aren't good at drawing 7-membered rings. So I usually draw 3 carbons and then 4 carbons, and I join them to make a clean 7-membered ring. Otherwise, you'll find the first time you try to draw a 7-membered ring, you accidentally draw a 6-membered ring. It's kind of tough. That's not what we care about. What we care about here is the amino group on cycloheptylamine. And so this one has 2 NH bonds to it. And if I look at all different kinds of IR spectra for primary amines that have 2 NHs on them, then what I'm going to find is that there's 2 of these little blips here. Whoops. So if you know it's an amine and you can see those stretches for the NHs, that's kind of helpful. There's not a lot of useful things you can do with IR spectroscopy, but that's actually a pretty useful thing if you know that there's an amino group in there. You got to be kind of careful when you're in the laboratory, or if you look at published spectra of amines, and that is the problem is that oftentimes when you get samples of amines, like if you make them in the chemistry 51 labs that we have here at UC Irvine, they're often contaminated with water, and it's hard to dry all the water out. And that water can leave huge blobs in your spectrum. Just a tiny, tiny amount of water contaminating your amine sample can make a huge blob. So you got to be careful about that, because it can sometimes hide those little NH blips from you. So you need really pure samples of your amine in order to reliably see these little blips that tell you how many types of NH stretches there are. Now, what about carbon-13 and proton NMR spectroscopy? those types of spectroscopy are just not that useful for telling you whether you have an amine air. Right? One of the most useful things is just looking at the molecular formula. So let's go ahead and take a look at some typical NH stretches for amines. So I'm going to go ahead and just draw out an amine. This would be an aniline. But if I take an aniline that has a ethyl group and a methyl group on there, when you look at the C13, carbon 13 resonances for these positions, right, here's an sp3 hybridized methyl group that shows up at 11.2 parts per million. Here's another sp3 hybridized group that shows up at 46.8 parts per million. Down here, here's a methyl group that's sp3 hybridized that shows up at 37. There's nothing distinctive about those. You can't tell whether those were bonded to nitrogen or carbon or oxygen, or you just can't tell. You have no indication from the chemical shift what it's bonded to, and that's typical. When you have things that are sp3 hybridized like this, they appear down below 100 ppm in the C13. You have no idea whether it's attached to nitrogen or carbon or oxygen. And you would see the same effect if I took some other alkylamines. Again, there's nothing about these C13 stretches that tells you that they were attached or close to an amino group. So the C13 is not useful for telling you whether the carbon is close to an amino group. That's not, unfortunately. Carbon NMR is pretty useful, but it doesn't tell you anything special about when you're looking at amines. The proton NMR is really not special either. The protons that are close to the amino group might be shifted a little bit downfield or to higher parts per million because of the electronegative amino group, but it's not a lot. The CHs that are next to those amino groups are not super special. The NH, if you take in the proton that's directly attached to the amino group, it can show anywhere in this region of, a little bit below 1 part per million to 5 parts per million. That could be an OH, it could be a CH. You have no idea when you see a signal between half a ppm and 5 ppm in that range. You don't know. There's nothing distinctive that allows you to say, oh yeah, that's an NH. That's a proton attached to a nitrogen. You'd never know. But I want to talk about splitting because there's an effect that makes it a little bit difficult to interpret. So I want to remind you that when you look at neighbors, the protons attached to oxygens hydrogen bond and bounce back and forth when they're hydrogen bonding so much that you can't reliably see splitting between neighbors and OHs. So if I had ethanol, right, what I would see is that that the protons here on the H3 are split into a triplet by the CH2 group. Right, the CH3 looks like a triplet because it's next to a CH2. And the CH2 group over here looks like a quartet because it's split by the methyl. But you don't see any splitting here for an alcoholoid because the OHs are typically hydrogen bonded. So it would only be under very special conditions where you could stop the hydrogen bonding, such as super unrealistically dilute solutions. So no splitting with OHs, and it's the same with amines. So that's all I really have to say is that amines have the same property because there's so much hydrogen bonding. Those H's don't, generally you don't see that kind of the splitting in the spectra that I will give to you in this class. So in the same way, this CH2 group that's right here is simply going to show up as a quartet. So let me just draw that out here. So that would just be a quartet. Quartet. I feel like I wrote the word quartet, so I've got to, I apologize for that. That's just going to freak me out if I leave that on there. That was supposed to be quartet. And again, over here, it's a quartet. That CH2 is a quartet. It's because it's split by the methyl. I wrote quartet again, but what's going on with my brain here? I'm sorry. Quartet. So again, there's no splitting over here from this, because usually under most of the conditions for the, doesn't split, and I'll say reliably. Are there some conditions where you could see splitting? Yeah, but no spectrum I give you in this class will have splitting due to an NH that's a neighbor. All right, that's all we can cover for today. We'll try to cover a little bit more about the background to amines, and then start to get into two aspects of amine reactivity: acid-base chemistry, and then reactions where the nitrogen atom acts as a nucleophile to attack other things. And I will see you on Wednesday. So go buy some CBD oil and see if you can synthesize some THC in your home using catalytic acid. Maybe you'll be successful.
Or till I'm stuck and my body feels weak. Headed down to the dungeon, wondering if they got some more. And if they don't, then I'ma have to settle for some draw. Better just stay cool, cause right on after I'ma have to go and continue on my mission, fishing for the yum.